Throughout chemistry, we find the recurring theme that structure helps to determine properties, whether it's valence electrons determining the chemical properties of an element, or the way that atoms are combined to form compounds that give them their properties. If we write the configuration for hydrogen, hydrogen is the very first element. It's got one electron, so it would simply have a configuration of 1s1. Right, and being that that is the only sublevel, the first main level is going to be the valence level, and so the s1 electron is the only valence electron, so therefore it has 1. Nitrogen, right, has 7 electrons, and so its configuration would be 1s2, 2s2, 2p3. And when we look at that, we see that the second main energy level is the outermost energy level, so the 2s electrons will be in the valence shell, as will the 2p, for a grand total of 5 valence electrons. When we use the noble gas shortcut, things get even easier to pick out valence electrons. Sulfur has 16 valence electrons. Its previous noble gas is neon, so if we put neon in brackets, and then we're going to pick up with 3s2, 3p4. And we see that pretty much all that's shown at the end here is those valence electrons in that valence shell. So sulfur would have a total of 6 valence electrons. Another way to get the number of valence electrons, kind of a shortcut, is to look at where the element's at on the periodic table. And we can use the group numbering to help us. So remember, hydrogen had a number of valence electrons equal to 1. And we see that hydrogen is in group 1. So there seems to be a relationship. All right, nitrogen had 5 valence electrons. So when we look at nitrogen, right, it's in group number 15. So it's not the whole number, but the ones digit seems to match up. Let's see if it works with sulfur. Sulfur had 6 valence electrons. It's in group 16. And sure enough, the ones digit, all right, is the number of valence electrons. Now, that shortcut, like most shortcuts, works only for certain elements, okay? Namely, the main group elements. So any elements in the first 2 columns and the last 6 columns. So the S or the P blocks, it'll work. If you're talking about elements that are in the D block or the F block, all of those are going to have 2 valence electrons, always. Remember that structure determines properties. So when we have a compound and we want to understand its structure or its shape to understand its properties, we need to first determine what that shape is going to be. And the first thing that we need to do is determine the orientation of the electrons in the molecule, because that's going to help us determine what the arrangement of the atoms is going to be. So the first thing that we need to do with our formula is determine what's going to be the central atom. Usually the central atom is going to be one of the first elements listed, plus a shape is going to have one center to it usually, or one focal point. And so whatever element there's only one of would be our central atom. So in this case that would be nitrogen. All right, the remaining elements that are in the formula would be surrounding that central atom. And it really doesn't matter exactly where you put them. We're just going to put them around the nitrogen. Okay, the next step is to determine the total number of valence electrons that you have to work with. So you can either do the electron configuration for each element, or you can use that shortcut that we just talked about. All right, nitrogen is going to have a total of 5 valence electrons. Each hydrogen has 1, but there's 3 of them, so we have to add 3 times 1 to that total for a grand total of 8 valence electrons. And so that's our pool of valence electrons to distribute. The next step is to take care of the bonding pairs, the shared pairs first. We need to connect the nitrogens and the hydrogens. A bond is created by 2 electrons being shared between 2 atoms to form covalent bonds. So we would put 2 here, we put 2 here, we put 2 here. All right, so that takes us down to 2. All right, the next thing that we do is we look to the outside atoms and make sure that they are taken care of. All right, and by taking care of, we mean stable, have a stable configuration. Usually we shoot for a full octet, but in this case, hydrogens can't hold a full octet because they don't have a p sublevel. So 2 electrons is the most that they can have, and that's what satisfies them. Well, the bonding electrons, the shared pairs, satisfy the hydrogens. So those are okay as they are. And so these remaining 2 electrons then end up as a lone pair or an unshared pair on the central atom. And so that would be your Lewis electron dot diagram for ammonia. Okay. Your dots might be a little cleaner, but yeah, you get the picture. We can do Lewis dot diagrams for particles that are charged as well, polyatomic ions. So here we have the phosphate ion, and so phosphorus is going to be our central atom, and we're going to surround that with the 4 oxygens. Okay, now we need to total up the valence electrons. So phosphorus is going to have 5 valence electrons because it's in group 15. Oxygen has 6 valence electrons each, and there's 4 of them, so we have to take 4 times 6. Now, this charge, we need to account for this charge, and whenever we have a -3 charge, whenever you have a negative charge, it means you have an excess of electron. So we actually have to add 3 to our total. And valence electron pools should always be an even number. So 5 plus 24 would be 29, plus 3 gives us 32. So we've got a lot of electrons to deal with. First place we put them is as shared pairs to create those bonds. The small dots seem to be working better here. So, all right, so that takes care of 8. So now we're down to 24. And remember that we need to satisfy the outer atoms first. And each of those atoms, the oxygens, needs 8 to be stable. So they need a full octet. And they're going to need 6 more each. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, there's 20, 21, 22, 23, 24. All right, and I realize some of the dots are smaller than others, but you see where they're supposed to go, okay? And that takes care of the 24. Now, the oxygens are all satisfied. They all have an octet, all right? And if we look at the central atom, we see that it also has an octet, okay? If the central atom is in the second row of the periodic table, okay, it has to have 8 valence electrons. If it's got, if your central atom is lower on the table, all right, from the third row on down, then you can get away with having either 8 or less than 8 or more than 8. But in this case, it's moot point because it is 8. And the only other thing that we would want to indicate, just like we did when we diagram our polyatomic ions in pictorial form, you want to show that the entire particle is carrying that -3 charge. So we would put the Lewis dot diagram in brackets with a -3. Now sometimes, and remember that I said that if the central atom is in row 2, you've got to have 8 electrons. So if we take a look at formaldehyde with the formula H2CO, the first element listed is hydrogen, but there's 2 of them. And hydrogen can never be a central atom because it can only form 1 bond. So we go to the next element, the one that there's only 1 of, and that would be carbon. Carbon can form up to 4 bonds, so that's a good candidate. So we'll put carbon in the middle, and we'll put our other atoms surrounding it. And so now we total up our valence electrons. All right, hydrogens have 1 each times 2, plus the 4 from carbon. Again, if you're not sure, you can either do the configuration or look at the group number, take the 1's digit. And oxygen is going to have 6 valence electrons for a grand total of 12 valence electrons to deal with. First place we put them is the bonding shared pairs, and that takes care of 6. Next place we go is around the outer atoms and making sure that they are all satisfied. Notice that 2 of them are hydrogen. They're satisfied by the bonding shared pairs. The oxygen, however, is going to need 8. It already has 2, so we need to put 6 more around it. And that takes up our stock of valence electrons. But now notice the problem here. Notice that carbon only has 6 valence electrons, and carbon is in row 2. Okay, so elements that are in row 2 as central atoms have to have the full octet. There's no negotiating that. So what that means for us is we're going to have to take the electrons we have. We can't just add any new electrons. We've got to reconfigure the ones that we have. And so what we're going to end up doing is taking one of these pairs and we're going to change it from being an unshared pair, a lone pair, to making it into a shared pair. Okay, and we can do that because we're not changing the total number of electrons we've got. We're just adjusting the distribution, if you will. Okay, so we're going to take that top pair and we're going to move it down here. So now there's 4 electrons between carbon and oxygen, and that creates what we call a double bond. Whenever you have 4 electrons being shared, okay, sometimes you'll see it written, it almost looks like an equal sign, it's 2 lines, okay, but that would be considered a double bond. And now you see that oxygen has its octet, carbon's got an octet as well, okay, because electrons that are shared between 2 atoms can be credited to both atoms. If we take hydrocyanic acid, HCN, we can see a similar phenomenon. All right. In this case, again, remember, hydrogen's not going to be our central atom. Carbon will be. And we'll just put the hydrogen and the nitrogen on either side. And if we take the valence electrons, hydrogen's got 1, carbon's got 4, nitrogen's got 5. And so when we add those up, we've got a total of 10 to deal with. Bonding electrons go in first. Okay, so that takes care of 4. We're down to 6. Take care of the outside atoms. Hydrogen's okay. Nitrogen needs 6 more to get its octet. So we've exhausted our pool of electrons, and nitrogen's happy and hydrogen's happy, but carbon most certainly is not. Carbon's in row 2. It needs to have an octet, but based on the current configuration, it only has 4. So just as we did in the last example, we're going to take one of those unshared pairs and shift it in and make it into a shared pair. So we'll take this out and we'll put that in there. Notice nitrogen still has 8 valence electrons, the 4 shared ones and the 2 unshared. But carbon only has 6. So if it worked once, let's do it again. So we'll shift another lone pair in. And so what we're going to do there then is create, all right, chop part of my nitrogen off there. Let's put that back in there. What we're going to do is create what we call a triple bond. So triple bonds are going to be consisting of 6 shared electrons between 2 atoms. And if you see it written in abbreviated notation, sometimes it would be 3 lines connecting those 2 atoms.